Hey everybody, today we're going to start talking about series. All right, we've been talking about sequences, doing some problems with sequences, and you know, sequences fairly easy. There's really not much to them other than just looking for a limit. What's kind of happening to these things as it goes forward. So today, we're going to be looking at moving from sequences to series. And how do we do that? Well, take the sequence, for example, 1, 1/2, 1/4, 1/8, 1/16, and so on. That's a sequence. To turn that into a series, all we have to do is really just replace all of those commas with addition signs, right? A series is just a sum. And in our case, we'll be looking at infinite sums, just like we looked at infinite series. And that's what the dot 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 happens to mean, right? Well, these series where we have, uh, you know, more generally, a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 and so on. This being an infinite series, it's how do you add together an infinite number of terms? How do we go out completely when there's an infinite number of them out there? Well, typically we're going to just go ahead and chop it off at, say, the nth term. Okay, so we would have a series a1 plus a sub 2 plus a sub 3 and so on until you'd get to a sub n, right? And that is often what we are going to call the nth partial sum. All right. Sometimes we'll even use a capital A sub n, or maybe even sometimes a capital S sub n as the nth partial sum. And basically what we mean by partial sums is, for example, the partial sum of 1 would just be the first term, right? Whereas a sub 2 would be like adding together the first two terms. And then a sub 3 would be equal to adding together the first three terms. And so on, right? We could keep going on and talk about these things as partial sums, right? And just like with sequences, we want to know, does this sum go somewhere, right? Is this sum infinite? When you add it together, does it shoot out to infinity and just get larger and larger and larger and larger? Does it go to, you know, what happens to this sum, right? Does it cozy up to a single value and like just get closer and closer and closer the more terms you add together? Kind of what happens as it goes along. So what I'm really asking is, does this sum tend towards some value? All right, that is a sub 1 plus a sub 2 plus a sub 3 and so on. That should be equal to the limit as n goes to infinity of this nth partial sum, adding up a sub 1 plus a sub 2 plus a sub 3 plus all the way up to a sub n. So as we add together more and more and more terms, does it look like it's tending towards something? Does it look like it's going to be equal, or at least get close to, infinitely close to, some value? Well, seeing as how this limit here that I just wrote down, okay? So let me get back here. Sorry, it's scroll around. So this, right? This limit over here, as we take that limit, we're going to be getting more and more and more and more terms. That's kind of tough to take a limit as we're doing the limit of more things added on, right? More sums and stuff. That's crazy to try and think about, right? But instead, what we can do is we can look at these partial sums here as we do more and more and more of them, right? We can actually turn those partial sums into a sequence. We can create a sequence of partial sums so that would be a sequence of a sub 1, and then the second partial sum, and then the third partial sum, and then the fourth partial sum, and so on, up to the nth partial sum. And we can try and take this sequence even further and see, does this sequence tend towards something? Does this sequence converge? Of course, if the partial sums as a sequence end up looking like they go somewhere, then we say that the actual series converges and heads somewhere, right? And so if I call this S sub n as the sequence of partial sums, we can define and say that the limit as n goes to infinity of that a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub n is going to be equal to the limit as n goes to infinity of this sequence of partial sums. All right? And that's what we're going to be looking to do in future videos and in future problems, is what happens to this sum. Does this sum stop or move closer and closer and closer to a particular value as you're adding more and more and more together? Or does this, shoot out to infinity and it doesn't necessarily converge to a value? Does it maybe add together and jump around wildly between values and not really tend towards anything? These are all questions we're going to end up taking a look at in future videos. Back to my original series that I posted, let me call it S, where we had the series 1 plus 1/2 plus 1/4 plus 1/8 and so on. I actually saw a really neat kind of proof of what this sum is equal to from, thank you, welcome back, Carter. But just to go through it really with you quickly, this is not a technique we're going to be using later on for evaluating these kind of series, but I thought it was kind of neat just to show you that even though we have an infinite number of objects here, 1/2, 1/4, 1/8, 1/16, and so on, this sum is actually going to equal something. If you were to be able to add together all infinite terms, you would actually get somewhere. You would actually get a finite, nice value if you added them together. Okay, so this is what they showed us in that show. Was if you take that S and you multiply it by 1/2. Well, then multiplying the other side of the equation by 1/2 would give you 1/2 plus 1/4 plus 1/8, and so on, right? And we're just multiplying and distributing through to every single one of those terms. Now, if we take that and we subtract it from the series above, that is 1s minus 1/2 of an s would of course be 1/2 of s. But on the other side of that, when you start subtracting, terms are going to cancel. 1/2 minus 1/2, that's going to go away. The 1/4 minus 1/4 are going to go away. 1/8 minus 1/8, that's going to go away. And so on. In fact, all of these terms going on out are going to cancel out, and we're only going to be left with the value of 1. Well, we know the half of something being equal to 1, that's just got to be equal to 2. All right? We're going to have different ways to prove this later on about why this sum is equal to 2, and we're not going to be using this method for future problems. However, I thought it was just kind of interesting, like a quick little way to show that an infinite sum can actually converge to a nice value that might be somewhat unexpected. All right? And so we're going to have a bunch of those things coming up in later videos and later problems. All right?